First, do you have any questions that you want to go over first, or any topics or concepts that you want to go over?
Nothing in specific, just basically what he's taught since the first content for the first midterm, like everything after the first midterm,
Oh,
basically.
everything after the first semester, like the alkyne chapter?
Yeah.
Yeah, okay. So the next chapter is the alkyne, which is the triple bond region. I mean not the triple bond region, the triple bond between two carbons right here, right? That is an alkyne,
Okay.
right? And there are two types of alkynes. There is a internal alkyne, and there is a terminal alkyne. Right? And internal alkyne, it can be split into two different things. It could be a symmetrical internal alkyne, or it could be asymmetrical, right? Where a symmetrical internal alkyne is, let's say we have a triple bond between these two carbons right here. This is symmetrical because we see that the two R groups are the same. They are both isopropyl groups, right? For asymmetrical internal alkynes, let's say we have a triple bond there. The two R groups are different. This is asymmetrical because this is an ethyl, this is a methyl.
Okay.
For terminal alkyne, the alkyne is at the end of the molecule, the terminal end, right? Where do you know what is attached to that terminal carbon right here? What else is attached to that terminal carbon?
Another hydrogen?
Right, another hydrogen. And that hydrogen right there is acidic, right? Meaning that if we use some kind of strong base like NaNH2, we can deprotonate that acidic hydrogen and give that carbon there a negative charge. And this negative charge right here can be your nucleophile or your base, right? Where this nucleophile can attack an electrophile or it can grab a hydrogen, a proton from an acid, right? Where this nucleophile here can do a lot of reactions. It could do, let's say we have this alkyne anion here. This alkyne with the negative charge is called an alkynyl anion. Anion meaning that there's a negative charge. Alkynyl meaning that the negative charge is on an alkyne carbon. There are five different reactions that could do. The first one is an acid-base reaction. So if you have H2O or H plus, that is an acid. What do you think that is going to do to this alkynyl anion here?
Protonate it, maybe?
Yep, that's right. Where that is just gonna go back to its terminal alkyne right here, right? Where the mechanism for that is that that negative charge, let's say our acid is H3O plus. That negative charge grabs that H, kicks out the water, and becomes this terminal alkyne here with the water side product. The second type of reaction we could have is, let's say, SN2. Right? Say we have this. What do you think is going to happen between this alkyne anion and this haloalkane here?
There'll probably be a substitution so that the bromine is added to it.
Right, so the bromine here is a leaving group. You notice how this carbon here is the positive charge?
Yeah.
We can say that that is the electrophile that is going to be attacked, and this is the nucleophile here that attacks that electrophile and kicks out the bromine.
Okay.
Right. So what that looks like is this right here, where we have that nucleophile, and let's say we have this electrophile star my nucleophile dot my electrophile. When I draw the attack, this negative charge carbon here attacks that carbon and kicks out that leaving group right there. When I do that, there's going to be a new bond between the star atom and the dot atom right there. That's the new bond from this attack, right? the Br minus gets kicked out and it's just floating around as a Br minus. But the dot atom here, it's still attached to that ethyl group right there. 1, 2, like that. SN2.
I see.
Right? So the next reaction you can have is E2. So if you have a secondary or tertiary haloalkane, like let's say this, then your reaction that is going to happen is E2 instead, where instead of this alkynyl anion acting as a nucleophile, that alkynyl anion is going to act as a base instead. So let's say we had a secondary haloalkane here. Um, what do you think is going to happen for elimination reactions? Like, what do we have to look out for? What kind of hydrogens? If this is an E2 reaction.
Beta hydrogens that could do a hydrate.
Uh-huh. Right. Beta hydrogens that could eliminate and form the double bond because that's the product of E2 reactions, forming some kind of pi bond, like a double bond, and kicking out the leaving group. Here are our two prospects, two different kind of beta hydrogens. Think of this as a small, unhindered, strong base. If that's the case, which beta hydrogen do you want to grab to make the more stable double bond?
The one on the right?
Right, the one on the right, because that is more substituted, which is gonna create that double bond and kick out that leaving group there. Those three arrows happen at the same time, concertedly, making that double bond right there, and that alkyne becomes terminal, where this hydrogen here that got grabbed is that hydrogen right there.
Okay, I see.
Uh-huh. And we have some Br minus floating around that got kicked out.
So is
Uh-huh.
the main product the one on the top that you just drew? Okay, I see.
Right, that's the main product, the double bond. Right.
Okay.
Okay. Now this last two reactions here, he skipped it in lecture, but he said he will go back to it at the end of the quarter. But let's just go over it now because the textbook introduced it at this time and it's like very similar on what we've been doing. But
Okay.
I'll walk you through this. The first one is some kind of carbonyl. Do you know what a carbonyl is on a molecule?
Um, C double bonded to O.
Right, C double bond O. So let's say we have some kind of random carbonyl like that, where this is the carbonyl part of the structure. This always has to have an acid workup step, like H2O, H3O plus, H2SO4 as a second step. Okay, let's write that down here. Number 4. Let's bring in the alkynyl anion and that carbonyl here. What do you think is going to happen between this alkynyl anion and this carbonyl here? What's our nucleophile? What's the electrophile? What's attacking? What's being attacked?
Would the nucleophile be the negative charge on the alkene, and then would would it be reacting with the O on the carbonyl with oxygen?
Yeah, this O here is partially negative, and this carbon here is partially positive. So this carbon here is the one being attacked right there, the partial
Okay.
positive carbon, right? And you're right, this negative charge here on the alkyne is a nucleophile, where that is going to attack that. But there's going to be a problem here because we're trying to make a new bond between that star and dot atom, but this dot atom already has 4 bonds. 1, 2, 3, 4. When we try to make a new bond, that's gonna have 5 bonds. So that breaks the octet rule. To maintain the octet rule, we have to move one of the double bonds onto oxygen like that, right? Where you know how a bond represents 2 electrons?
Hmm.
Those 2 electrons are gonna go to the oxygen right there. So let's just draw what we are going to get first. This is the star. This is the dot. Now this is important where we attach what is attached to the dot carbon. That dot carbon is attached to an ethyl group, a methyl group, and no longer a double bond oxygen. Right. So let's just draw that ethyl group there, methyl group there, but now it's a single bond O minus. Right. Because before this oxygen here has 2 lone pairs of electrons, but now it has 3 lone pairs of electrons. It gained another lone pair from that bond right here.
Okay. Where does the other ethyl come or methyl come from on the dot?
Right. This methyl group here is this methyl group there.
Oh, I see.
Uh-huh.
Okay.
Right. And this ethyl group here is this ethyl group. That dot is no longer double bonded to the O. It's
Mhm.
single bonded to the O minus now.
Okay.
Right.
Okay.
Uh-huh. Now, the last step, which is why we brought in the second step acid workup, some kind of acid like H2SO4, H2O, H3O plus proton source is going to protonate the O minus and become alcohol. Like that. Okay. The last one is a 118A kind of reaction. So this one here is a neo reaction. The last one is epoxide. So let's say we have this epoxide here, first step, second step, acid workup. If you have a negative charge solution, then you are in basic conditions. Because you could think of it as like this negative charge here wants to get quenched, wants to become neutral. And the way that I could do that is either attacking an electrophile and making a new bond, or getting protonated, grabbing an H plus, which is why we are in basic conditions. And in basic conditions, do you remember if we want to attack the more or less subside of the epoxide?
Was it the less substituted side?
Right, the less substituted side because it wants to attack the less sterically hindered side for basic conditions. That's right. When that happens, that cracks open the epoxide like that. Star my attacking atom, dot my atom being attacked, make that new connection between them, star and dot. This is the new bond between them. Now I draw what's attached to the dot atom, which is, I'm gonna make this easier to see. This carbon here that I'm highlighting purple is gonna be that carbon right there. That's purple. Where this bond there is that bond right there.
Okay.
That highlighted purple bond is attached to a wedged methyl, and this oxygen here, but now it is negatively charged because this bond got broken, and that bond, two electrons, went onto that oxygen right there, giving that oxygen a negative charge.
Okay.
And the last step is the acid workup. Protonate that O minus to become alcohol right there. Does this make sense here?
Yeah, that part makes sense.
Okay, okay. Now I'm gonna give you five different predictive product questions based on these reactions. Are
Okay.
you okay with the whiteboard? Using the whiteboard on Zoom?
Oh yeah. Oh,
Uh-huh.
I've actually never done that before, but I can try.
Okay, okay. Let's see. Let me. Do you have an iPad that you could connect the Zoom with?
Yeah, I do actually.
Uh-huh. Yeah, I think that would be easier. So then you could like, draw easier on the with the Apple Pencil instead of the the mouse trackpad or mouse.
Okay. Do I, how should I do that?
Yeah, you could go to your iPad, go to the email, and then click on the Zoom link I sent you, and then it should join on your iPad if you have the Zoom app.
Okay. Let me
Yeah.
see.
Uh-huh. And then while you do that, I will make the practice problems now.
Okay. Okay, I'm in the lobby for
Oh, I see. I see.
Recording in progress.
oops.
Oh yeah. When you join from your iPad, click no audio. When it asks you to join with audio, yeah, click no audio.
Okay, I think that's working now.
Okay, let's just try these first two first. Because I think we need space to do the mechanism as well, and
Okay,
then we'll move on to the next ones.
okay. Let's see. So do I wait, so I just write. Oh, I just write on it. That's crazy.
Yeah.
Okay. So is this like one of the first reactions?
Right. So we have a terminal alkyne here with a hydrogen there. And what is this first step going to do with that hydrogen right there? So I would draw out that hydrogen explicitly and draw out the NH2 minus floating around nearby, that H.
So here.
Right. Uh-huh. And then this NaNH2 here, yep, is that NH2 minus, which is a strong base. Right. Uh-huh. And what would that strong base do with this acidic hydrogen here?
Does it deprotonate it?
Yeah, it's gonna deprotonate it. So let's draw that arrow from the N minus, grabbing that hydrogen, and then that bond between that carbon and hydrogen right there goes onto that carbon right there. Now let's draw in the intermediate, the product of the first reaction.
Okay. Oh, I can change color.
Yeah.
So here, is it still a triple bond there?
Yeah, still triple bond there, but now there's a charge on that carbon, negative charge, right? Which is a nucleophile or base. Now we bring in our second
Okay.
step.
And this is here. And then I'm gonna do the thing you said. So this would be the star, and then
Right. So which carbon is negatively charged? Is it this part of the alkyne or is it this part of the alkyne?
the second one.
Yeah, so this is the starred atom here, the one that is negatively charged. That's the one that is going to be the nucleophile.
Okay.
Right, that's the starred. And we dot the positive charge carbon on this side here.
Would it be this one right here?
Yeah, it would be that one, right? And methyl group. Yep. Now let's do this SN2 reaction where this is our nucleophile. This is our electrophile. For SN2, the nucleophile attacks the electrophile and kicks out the leaving group. And now we connect the two groups together.
Like that?
Right, right. So let's star this carbon right here, which is that star carbon, and then let's dot that carbon right there, because that's the one being attacked. That's the new bond right there. This
Oh,
dot carbon, yeah, is not attached to two groups. It's attached to one group, which is a CH2, and then right after that CH2 are the two methyl groups.
Okay, my Apple Pencil just died. I'm
Oh,
sorry.
I see. That's okay. It's okay. Where
I'm gonna charge it really quick.
see. Um,
So after the dot is just what's connected to the dot on the on oh,
electrophile on this molecule here, right?
okay, I see.
Because after the dot here is a CH2, which is that CH2, and then
Mhm.
after that CH2 is this isopropyl group, which is the isopropyl group there. So the star and dot technique is like good to like keep track of all the groups. It makes sure you don't put like the groups on the wrong spot, or like you lose a carbon or add an extra carbon by accident.
Mhm.
You make sure you keep track of everything, right?
Okay.
Right. That is the answer for the first reaction. The second reaction here, let's say we know the first step is going to be the exact same. The NH2 minus grabs that hydrogen, makes that alkyne anion here. Okay. Now, can you tell me what is going to happen between that alkyne anion and this carbonyl?
Um, does the positively charged carbon on the alkyl attack the negatively charged carbon on the alkyl
Oh,
attack
alkyne.
alkyne, sorry,
Wait.
attacks the positively charged carbon.
Yes. And then what else moves after that attack?
And then the one of the bonds on the double bond to the oxygen goes to the oxygen.
Yes. That's right. Where this is uh really useful, like the star and dot technique to keep track of everything that's attached to the dot. So we know that we make a new bond between the star and the dot, which is that new bond right there. That dot, what is that dot attached to?
It's attached to um another hydrogen, an
Uh-huh.
oxygen, and then um a methyl, and then after that, or an ethyl, and then after that, two methyls.
Wait, tert-butyl. So it is attached to like this tert-butyl here is that tert-butyl right there,
Mhm.
right? And the hydrogen we can leave as invisible, but what charge would the oxygen have on that dot now?
Negative charge.
Right, negative charge, and it's no longer a double bond. It's now a single bond.
Okay.
Now, what will happen in the third step?
The oxygen attacks the hydrogen, and then it makes alcohol.
Right, that is it. Final answer here. Okay, let me screenshot this so I can post it to your notes. Now, let's do 3 more reactions on this. Let's say we have that. Second step, say we get that. And then the last one, let's do Okay, let's try these three reactions here.
Okay. Okay, so for the first one. Here.
That's right. First step, acid-base reaction. The strong base NH2 minus deprotonates the alkyne hydrogen and gives us this negative charge alkyne anion, which can be a nucleophile or base. Now let's bring in our second step of H3O plus, some kind of acid. It could have been H2SO4, H2O, but a proton source, H plus source.
Okay. And then doesn't this just turn into
Yeah, that's it. Where basically like no reaction happened because like that's the exact same starting material we had. The product is the same thing as the starting material. So you could say no reaction happened, but a reaction did happen. It just got deprotonated and protonated again, but like it gives you the exact same thing, but you started with.
Okay, gotcha.
Yeah.
And then this would be the same. Would that be the carbon?
So this is a secondary halocane. So our reaction here is going to be E2,
E2,
not
I see.
SN2. So for E2, let's locate our beta hydrogens. Right. Now we choose the one that is the most substituted to do the E2 reaction.
So this one?
Right. The negative charge here is going to act as a base now, not a nucleophile. It's going to grab that hydrogen, make a double bond, kick out the leaving group. Right.
This becomes, oh, and then it attaches here? Or what's after that? Like, how do I attach it to?
Right. So let's draw that triple bond again. The negative charge on that triple bond grab the H. So that becomes this structure again with the H right there.
Mhm.
Right. And then what would this structure look like now after we did the E2 reaction? Right. Double bond right there. No more bond here because we kicked that bond
Wait,
out. Right. Yeah, that's the answer. Where this is the main product here, that E2 product, the double bond product.
oh, that's it?
Yeah, that's it.
Oh, okay, so it's not attaching to the cyclopentane.
Yeah, these are not connected. They're separate.
Okay, I see, I see.
Right. Where acid-base reaction, this just grabs the H.
Oops.
All the other ones we did were like nucleophile attached to electrophile, but this is acid-base reaction. This is also acid-base reaction here.
Okay, I see.
Uh-huh.
And then is this acidic conditions or basic?
Right. So if we have a negative charge, it is going to be basic conditions because that negative charge wants to be neutralized by either grabbing a an acid or attacking something like that electrophile right there. Right. Right, right. And this will invert stereochemistry because it does like a backside-like mechanism. So
Mhm.
that wedge will invert into a
dash.
right.
Okay, so then this is, and then is this the?
Yeah, that's the dot. And I would draw out this as the template first, like draw out that epoxide backbone. And yeah, that's the dash bond where this is the dot carbon right here. This is the star carbon, where that star carbon is still triple bonded.
Oh, okay. Triple bonded to.
Right, triple bond to that star right there. And then that triple bond is attached to 1, 2, 3 propyl group. 1, 2, 3. Yeah, that's right. Now we just draw what is attached to this carbon right here, which is an O minus and that dash methyl. Right. Now we bring in our third reaction.
H2O.
Mhm.
So is this gonna go there?
Other way. The O minus attack the H and kick out the conjugate base. Right. And then kick out the OH, where it would be more clear to see it if we drew it like this. Like let's say we had H2O like that. It could grab that H and it kicks out that to become OH minus like that. But this is the
Okay.
same thing.
And then this becomes an alcohol.
Yeah, and then that becomes an alcohol.
Oh, I guess I don't have to redraw it, but yeah.
Right.
Whoops.
Oh,
Oh my God.
whoa. What the heck? Like that. Final answer.
Okay, great.
Where the hardest reactions are probably the epoxide opening ones and the carbonyl ones.
Mhm.
The other ones, acid base, that's probably the easiest one. And then SN2 and then E2 is a little bit tricky because like you have to recognize that our substrate is secondary halokane, and that's how you know it's E2. Screenshot that. Okay, so now let's go over the next set of reactions for alkynes. Which are going to be reduction reactions. Right. So let's first go over the one with H2 PDC first. So a review of this, let's say we had an alkene like that, and we put that through H2 PDC. What would that reaction do to that alkene?
It would just have hydrogen on both sides of the double bond and on the same side.
Yeah, that's right, on the same side. Where it could be both wedge or dash, but in this case, since these are not going to be chiral centers, we could just leave them out as invisible. But you're right, they would be on the same side, right? Where now let's introduce a triple bond. If we do H2 PDC, let me just write out those hydrogens to make it clear. Where these two hydrogens are these two hydrogens here. Right. That H2 PDC will also attach two hydrogens on the alkyne on the same side. It's still syn addition, where I like to number my molecule to keep track of everything. So this is 1, 2, 3, 4, 5. The intermediate here is going to look something like this. 1, 2, 3, 4, 5. The reason why it is a cis alkene into intermediate is because we said that this reaction does syn addition. The hydrogens have to be on the same side, which is why they are cis to each other, making the other groups cis to each other as well. Right?
Okay.
But it doesn't stop there. H2 with this kind of metal catalyst is overreactive. It will keep going until the alkane, the single bond. So if you see a triple bond, which is between 2 and 3, that would become a single bond if you put that through H2 PDC there. Right? Where this is just the intermediate of like what happens before that.
Uh-huh.
Now, let's say you wanted to stop at the cis alkene here, right? Do you remember what kind of reagent that you have to use if you wanted to stop at the cis alkene?
No, not at the top of my head.
Uh-huh. Right. So that reagent is H2, but not PDC because PDC will make it overreactive. We want to use a poisoned version of it, like that will slow down the reaction. The poisoned version of it is Lindlar's catalyst. So when you see Lindlar's catalyst, think of a poisoned catalyst that slows down reaction and stops at the cis alkene. Right. And it stops at cis alkene. H2PDC goes all the way down to alkane. Okay. Now, let's say you wanted to make the trans alkene. Right. 1, 2, 3, 4, 5. To make the trans alkene, you want to use a reaction called dissolving metal reduction, which you are going to use either sodium metal, 2 equivalents of it, or excess in ammonia liquid, NH3 liquid, like that. These set of reagents would make your trans alkene. So here's a flowchart of what we just did. Let's say we had that alkyne. Let's say we put that through H2 PDC, H2 Lindlar's cat, and Na metal 2 EQ, NH3 liquid. What would the first reaction do to this alkyne here?
It would make it into an alkane with
Yep.
single.
Uh-huh. That's right. And what would the second reaction do to this alkyne?
It would make it into a double bond and cis on the same
Y-
side.
Uh-huh. That's right. And the last one would make it
Trans.
yes. Okay. So that is the summary of the reduction reactions of alkyne right there.
Okay. Is it only those three for reduction?
Yes. And other than PDC, you could also see PT or rainy nickel, right? But it was just these three for now. And I think for all of 118 as well, just these three. H2, some kind of metal catalyst, H2 Lindlar's cat. And instead of sodium, you could see lithium as well. So if you see sodium or lithium, it would do the same thing.
Okay, gotcha.
Right. Now let's bring these reactions together on what we learned today, and try to do some synthesis problems.
Okay.
Okay. So let's say let's start with this. Okay. Yeah, just think about this synthesis problem, and let me know, how would you approach the synthesis problem? Like, what would you do first? Or if you want to go backwards, what do you think the last step is going to be? Or you could just tell me what you think the first step is going to be. Either way works.
Um, I'd probably do an SN2 reaction first to add
Mm-hmm.
the alkane chain,
Right, right.
and then after that,
But
um,
how can we make this alkyne a good nucleophile for SN2?
oh right, we have to deprotonate it first. So use acidic condition like H2O or H plus.
Not acidic conditions, basic
Basic,
conditions
sorry.
to
Oops.
deprotonate the um terminal alkyne and
Mhm.
make that negative, right? Now, what kind of electrophile? It's basically just this R group with a good leaving group, like bromine, like that, right? Which will attach that R group there, where this is the star, this is the dot, this is the star, this is the dot, like that. Does that make sense?
Yeah.
Okay. Now, how can we convert that into this?
You would use H2 and then Lindlar's catalyst.
Yes, that's right. That's the synthesis. Where the first step was acid-base reaction. The second step was SN2. The third step is reduction to cis alkene. Right. We want to try another one?
Yeah, for sure.
Let's do it. Okay. This is gonna involve some alkene reactions from last midterm two, last chapter two.
Okay. Um, oh, I see. So first, do we deprotonate the triple bond to make it a good nucleophile?
Yes. That's right.
Okay. Oh, okay. I think I kind of see it. And then do we do SN2 to add an alkane chain?
Right. Which we want to add that alkane chain right there,
Right.
which is that.
And then do we make the triple bond into a double bond by using oh no, this is trans. It'd be trans, so we'd use like sodium and NH3.
Yes, sodium NH3, and we need at least two equivalents of it. You can say sodium excess or two equivalents, but make sure you put two EQ or excess.
Okay, and then that should make it into like into double bond. And then I think after that, is it the dihydroxy addition with
Yeah,
OH?
you got it. Nice, nice.
And then which adds OH to both sides.
On the same sides in addition. Right. Yay, you got it.
Yay!
First reaction was acid-base to deprotonate that and make the nucleophile. Second reaction, SN2 to extend the molecule by alkyl chain. The third reaction was the new reaction we learned, reduction to trans alkene. And then the last reaction was a last material, dihydroxylation. Yes. Okay, 1, 2, 3, 4 step synthesis, but Pascal, he gives usually like two-step synthesis, like for his practice exam and his actual exam, like it was like 2 or 3 steps. But yeah, you're gonna you were able to understand like this, right? Like how we transform this reactant to the product. Yeah, that's good. That's good.
Yeah.
Okay. Want to do more synthesis problems that would combine these together, or you want to move on to the next alkyne reaction?
Let's see. We could probably, I think we can move on to the next one really quick.
Okay. Yeah, let's move on to the next one. Where now, let's see, what's the next one? Okay, addition of HX. Okay. So say addition of HX. Let's have a review. We have that alkene and we put that through HBr. What is going to be the product?
Okay, HBr. Doesn't the BR just get added onto it?
Right. On which one though? This one or this one?
The first one?
Yep, the first one, the Markovnikov one. That's right, that's right. Mhm. Because the mechanism is that we want to form the carbocation on the more subside. So that means the less subside has to grab that hydrogen, form a carbocation there. There's no rearrangement step here, no hydrate or methyl shift because that's already at its most stable position it could be at, where the Br minus can come in and attack that positive charge and give us that right there. This is gonna be the exact same mechanism and reaction for the alkyne, but 2 times. And there's different types of alkynes that you could have. Let's say you had a terminal alkyne. You're going to get one product. Right. If you have a symmetrical internal alkyne, you're also going to get one product. But if you have an asymmetrical internal alkyne, then you're going to get a mix of 2 products. And for this reaction here, you need, let's say, at least 2 equivalents to go all the way through. Need 2 plus EQ. Okay, let's look at the terminal alkyne situation like that. And we have 2 EQs of HBr. We know that the more subside is this one, which is why we are going to protonate the less subside, kick out the Br. That gives this right here, where this gains a hydrogen. This carbon here lost the bond, which is why it has a positive charge. The Br minus comes in, attacks that positive charge, becomes this product here. This was our first EQ, the first equivalence. If he gives you first EQ, only one EQ on the reaction, you stop here. You stop there as your answer because we don't have any HBr, any more HBr if you have only one EQ. But if you have 2 EQ, or I think you could just assume excess if you have like HBr, that instruction is supposed to assume excess. Like you don't even have to see 2 EQ or excess. You can just assume it's excess. The second one is going to do the exact same thing. But now the answer is going to give you a geminal dihalide. Geminal meaning that the 2 halogens are on the same carbon like that, right? Where that's the only product we have right there for terminal. For internal, there's symmetrical. Like let's say we have this one.
Oh, wait, sorry. Can you scroll up for like 1 second?
Yeah.
Thank you.
Yeah.
I lost the last part. Okay. Okay, thank you.
Yeah. Where for internal, let's say we have an excess amount of HBr or 2EQ. Let's say this is 1, 2, 3, 4, 5, 6. Our product is always going to be geminal dihalide on the more substituted side of the alkyne. But this internal alkyne here, they're both equally substituted, so it doesn't matter which carbon it attaches. And it doesn't matter too because you know how this is symmetrical? They're 2 of the same R groups. 2, 3, 4, 5, 6. it could be at carbon 3 or 4, but that's gonna be the exact same product. So that's our only product right there. If you try drawing this product right here, where the BR attaches to the other side, that's the exact same thing as that. It's just flipped or rotated. Right? It goes through the same exact mechanism as this right here, where we know that the product forms a geminal dihalide on one of the carbons of the alkyne there. Right? But since this is both equally substituted and they're symmetrical, it only gives us one product. But now let's say we had an asymmetrical alkyne like that, we get two products, where it does matter now where you attach the two BRs. You could get that product, or you could get this product here, where these are now different constitutional isomers because the R groups were not the same, so that's why you get two separate different molecules there for asymmetrical internal alkyne.
Okay, I see.
Yep, and that is it.
Okay, sounds good.
Yeah. Any other questions?
No, not at the moment, but I'll let you know if I have some.
Okay, sounds good.
Thank you.
No problem. I'll see you.
I'll see you.